Assalamu alaikum dear students, welcome to the lecture of the classical mechanics. In this lecture we will discuss the solution for the problem number 7.4. If I minimize this so that I can write it legibly. Yes. A particle moves in a plane under the influence of a force F is equal to minus AR power alpha minus 1 directed toward the center. Means the force is acting on the particle and particle moving in under the influence of that force where A and alpha are constant. Okay. Choose appropriate generalized coordinates and let the potential energy to be zero at the origin. Okay. Find the Lagrangian equation of the motion. Okay. Is the angular momentum about the origin conserved? Is the total energy conserved? Okay, the first thing is that we have to find the uh, total generalized coordinates, and then we will find the Lagrangian. For Lagrangian we will require kinetic energy and potential energy, because potential energy, the force is given, we can find the potential energy from this if the force is some type of conservative force. So if we go to solution, this the kinetic energy of the particle is given by, you know that when particle move in two dimension, kinetic energy will be equal to m over 2x dot square plus y dot square, and we convert we can convert this Cartesian coordinate into polar coordinate, so it will become m over 2 r dot square plus r square theta dot square. You know that if x is equal to r cos of theta and y is equal to r sine of theta, and we can take its dot product and derivatives, and then we can add them. It will give 1 over 2 r dot square plus r square theta dot square. And the potential energy of the particle, you know that potential energy is equal to minus f dot dr, and f is given minus a over r, so its integration will lead to potential energy which is equal to a over r, a over alpha into r power alpha. Then Lagrangian of the system will be equal to T minus U. So kinetic energy is this. This is kinetic energy minus potential energy. Potential energy is equal to A over alpha power R power alpha. This is potential energy. So Lagrangian is equal to T minus U. We have put the kinetic energy expression and potential energy expression in the Lagrangian. Then by substitution in the Lagrangian equation, we have, when we know that when we put this Lagrangian into Lagrange equation, which is d over dt partial L over partial theta dot minus partial L over partial theta, which is equal to 0 for first, and then d over dt partial L over partial r dot minus partial L over partial r is equal to 0. We will put this Lagrangian equation into this whole equations, and then we'll put this Lagrangian into this whole equation. It will give us two solutions. For the generalized coordinate r, means for when we put this Lagrangian into this equation, it will give us mr double dot minus mr theta dot plus a r power alpha minus 1. Okay, when we put this equation into this, it will give us for the generalized code theta, this will give us d over dt mr square theta dot is equal to 0. We have obtained these two equations, one for generalized coordinate r and the second for generalized coordinate theta. Since the angular momentum is defined, we can define the angular momentum L. L is equal to mr square theta dot. You know that angular momentum is equal to I omega, and I is equal to mr square, and this omega is theta dot. So angular momentum can be written as mr square theta dot. The total angular momentum is conserved in accordance to Lagrange equation. Thus we have, therefore the angular momentum is conserved in accordance to, because that if we look back to this equation, the derivative of the total angular momentum is 0, d over dt we have now discussed that angular momentum is equal to mr square and theta dot, as we know that L is equal to I omega, I is equal to mr square and omega is equal to theta dot. So mr square theta dot, so d over dt, and this is angular momentum, so dl over dt is equal to 0. It means this thing is conserved, this thing is constant, and when this will be conserved, it means that its derivative will be equal to 0. Here we discussed this point. Thus, therefore, the angular momentum is conserved in accordance with the Lagrange equation. Thus, we have mr dot minus L square over mr square plus A over r. So we can put this values, use this equation in the equation for the radial equations. In this equation, if we put the value of this theta dot in, this will give mr dot double dot minus L square over mr square r cube plus ar power alpha minus 1 is equal to 0. To take the calculation more easier, we multiply this by r dot, so that if we multiply this whole equation by r dot, so it will give like this, r dot. We have multiplied this whole equation by r dot, which is simple, the time derivative of the mechanical energy. The first term is the time derivative of the mechanical energy, d over dt mr dot square, mr dot square, this term. And for the second term, this can be written d over dt L square over 2 mr square, and this is d over dt E over r power alpha 1. So it can be written as kinetic energy plus potential energy. This because this is the rotational kinetic energy and this is the translational kinetic energy. So d over dt translational kinetic energy plus potential energy. So when the total time rate of energy is equal to 0, it means total mechanical energy is also conserved. So our both law, total law of conservation of the angular momentum is also satisfied, and law of conservation of energy is also satisfied. We are looking at dl over dt is equal to 0, and de over dt is equal to 0. So law of conservation, momentum is also conserved and energy is also conserved. There is no change in the total energy, and there is no total change in the total angular momentum. So I will stop at this point.